In this video, we'll look at the remaining questions in section 5.3 on Achieve, questions 31 through 39. For 31 here, it's another one of these where we have the initial value problem. So showing you the work that I did for this one, I'll bring this up a little bit where I can show some more work. For 31, we have the derivative given, and again, it doesn't matter whether you call it dy dt or y prime. I said y prime is 5 on the root of t. We know that the original function evaluated at 1 is equal to 4. And please remember, they give you that information in order to get rid of c. So now when I find the general antiderivative, I know that this is the same thing as 5 times t to the 1/2. So when I add 1 to that exponent, I'm going to get 5t to the 3/2 power. And then we divide by that new exponent of 3/2 plus the constant of integration. If I simplify that, this is 5 times 2/3, which is 10/3. And then I went ahead and wrote this as the square root of t to the 3rd power, since the original was in terms of radicals. Plus our constant of integration. Now the goal is to get rid of that constant of integration. Well, I can, because I know if I evaluate this function at 1, I'm just going to get 10/3 times 1 over here, which is just 10/3, plus c has to equal 4. Well, I know 4 is the same thing as 12/3. 12/3 minus 10/3, it's going to leave me that c is equal to 2/3. Therefore, I know that the original function in this problem is just 10 on the square root of t cubed over 3 plus 2/3. And in fact, for the answer I put here on Achieve, I'll see if I can't just make that all one nice fraction here. I'll say I have, let's bring this in here, the fraction where the numerator is going to be 10 on the square root of t to the 3rd power, t raised to the 3rd. And then we have outside of that square root, we're adding 2. And all of that should be over 3. So that's the same answer as what I have here. I just went ahead and collected a common denominator. Sometimes Achieve is a little picky about the format of the answers. Let's see if it likes the format of this answer. I'll hit check answer, and it liked it just fine. So now I'll say, I'll go on to the next question here. For that next question, again, I'm given an initial value problem. This time I have the group 7x plus 2 to the 3rd power. And I know that the original function evaluated at 0 is 3. So what I did here, again, remember, anytime you have a group to a power, if you were taking the derivative, you'd say the power comes down in front times the group left alone to the one lower power times the derivative of the inside. Well, we do the opposite of that. We say leave that group alone, but raise the power by 1, so it goes to the 4th power, divide by that new power, and divide by the derivative of the inside. So I'm dividing by 28 down in that denominator, plus our constant of integration. So before I went to the final answer, I needed to find out what c was. In order to determine that, you'd plug a 0 into your function. When you do, you can see your numerator is still going to be 2 to the 4th power. Your denominator, of course, is 28. You'll have 16/28 plus c is equal to 3. So I went ahead and simplified. 16/28 is the same thing as 4/7. 4/7 plus c is 3. I know 3 is the same thing as 21/7. 21/7 minus 4/7 gave me c is equal to 17/7. So now I got my final answer here of 1/28 times this group 7x plus 2 to the 4th power. And I'll say times the group 7x plus 2. And then that group is raised to the 4th power. And then we have plus 17/7. Should be a great final answer here. We'll check that. Yeah, absolutely. Next question. For 33, again, an initial value problem. They're really wanting to make sure you get this concept down. We say, well, okay, no problem. We know that this original problem, 8 sine x, the integral of sine is going to be the negative cosine, since the derivative of negative cosine is sine. So the derivative of the integral of 8 sine x is going to be negative 8 cosine x plus the constant of integration. Now, in order to get rid of that constant of integration, I just need to say, well, let's evaluate this original function at pi over 2. When I do, it's easy because the cosine of pi over 2 is 0. So that just gives me 0 plus c is 2. Thus, I can see that the constant of integration is 2. And thus, my original function is going to be negative 8 cosine of x and then plus 2. Check that. And Achieve says absolutely. For the next one, we have an exponential function as the initial value problem where the first derivative is given. So if I know that the first derivative is e to the x, I know the original function is also e to the x because the derivative of any exponential function is an exponential function. So the integral of e to the x is e to the x plus the constant of integration. But now I know that I can solve for that constant of integration by plugging 4 into this equation. I can say, well, when I do that, I'll get e to the 4th power plus c has to equal 8. That allows me to solve for the constant of integration and say it's just going to be 8 minus e to the 4th there. So therefore, whenever you substitute what c is in the place of c in your answer, you should get y equals, and they want an exact answer here. If they want a decimal approximation, they would always say round to so many decimal places. So since it does not say that, I know it wants this exact answer, e raised to the x. So please don't type into a calculator what 8 minus e to the negative 4th is. It's not wanting that. I'll just put plus 8 minus e raised to the 4th. And this should be exactly what it wants. It is. When we look at the next problem here. So I like this one because now, yes, it's an initial value problem, but it's a 2-step initial value problem, twice the fun. So they're giving me the second derivative and asking me for the original function, given information about the first derivative and the original function. In this case, the first derivative evaluated at 0 is 12, and the original function evaluated at 0 is 2. That's going to be extremely helpful for a polynomial function because I know that anytime I plug in a 0, all of the x terms are just going to cancel. So I already know my values of c are going to be 12 and 2 before I even work the problem. But to show you that, whenever I integrate 54x, it would become 54x to the second over 2, or 27x squared, plus c. Now, I already know that c is 12 because if I plug a 0 into this equation, that first term cancels out. And so you'd say, well, then c has to equal 12. So I'll go ahead and say, well, I know my first derivative then is 27x squared plus 12. The original function has to be the integral of this. The integral of 27x to the second would be 27x to the third over 3. That's where the 9x cubed comes from. The 12x, this is understood to be 12x to the 0, so the integral becomes 12x to the first plus our constant of integration. Again, whenever you're given f of 0 is 2 for a polynomial function, you know that the value of c has to be 2 because when you plug a 0 into these two terms, you get a 0, thus c is equal to 2. And so I have my first derivative and my original function. The first derivative here, 27 x raised to the second power plus 12. And then the original function, 9x raised to the third. Whoops, I thought I was typing it in. Ooh, I was in the wrong place. Let me fix that. Down here, 9x raised to the third. And then we have plus 12x plus 2. I started to put plus c. We don't want the c's in there. And we shall see if this is right. And of course it is. So now you're thinking, well, hey, these are pretty straightforward, pretty easy. They are. One more like this. This time, again, we're given a polynomial function for, oh, sorry, still on this page, not 37, 36. Again, we're given a polynomial function. This time has 3 terms, makes it a little bit more interesting. So you have x cubed minus 16x plus 10. We're trying to integrate that 2 times to get to the original function. You know that the first derivative evaluated at 0 is 3, and you know that the original function evaluated at 0 is 10. Instantly, I know that that means the first value that I get for c when I find the first derivative, it's 3. The second value that I get for c when I'm trying to evaluate the original function will be 10, because any polynomial function evaluated at the terms of x of 0, they're all just going to cancel, and so you'll have c is equal to 3 and c is equal to 10. So I went ahead and just did that in this problem. I said, well, the first derivative, x cubed becomes x to the 4th over 4, or 1/4 x to the 4th. 16x would become minus 16x to the 2nd over 2, minus 8x squared. This is your plus 10x. And again, if you evaluate this at 0, you would just get c, thus c has to equal 3. Now we're integrating that to get back to the original function. The integral of 1/4 x to the 4th, the x to the 4th goes to x to the 5th. You divide by 5 for the 1/4 to become 1 over 20. Then we can say this is going to become minus 8x to the 3rd over 3, minus 8/3 x cubed. Then we have the integral of 10x becomes 10x to the 2nd over 2. And we say that's where the 5x squared comes from there. The integral of 3 is 3x, and then our constant of integration has to be the value of 10, because again, when you plug a 0 in, all of those terms cancel, meaning c has to equal whatever terms on the right-hand side, in this case 10. So now we plug this information in. We'll have our 1/4 x raised to the 4th, and then minus 8x raised to the 2nd, plus 10x plus 3, whoops, for the first answer. And then the second answer here, we have our 1 over 20. And let me move this down to where I'm showing that a little bit better. 1 over 20x raised to the 5th power. And you will probably be a little quicker about inputting these answers in here. The laptop I'm doing these videos in is not ideal for data entry. Doesn't have a separate keypad for numbers and stuff. 5x raised to the 2nd plus 3x and plus 10. So now I believe that those are entered in correctly. Let's see. Absolutely. For 37 here, this was the one I almost jumped the gun on and did for my last example. So this one's asking me to look at t to the negative 3 over 2 power. And I know that that's pretty easily integrable. I'll still just use the power rule. I know that the original function evaluated at 25 is 2. And I know that, sorry, the first derivative evaluated at 25 is 2, and that the original function evaluated at 25 is actually 3. So now, using that information in order to solve the problem, I'll say, well, let's take the integral one time to get to the first derivative. The integral of t to the negative 3 over 2 would become t to the negative 1 over 2, and then you would divide by negative 1/2. But if you divide by negative 1 over 2, then you're multiplying by negative 2. I just went ahead and said it's better to put negative 2 times t to the negative 1/2. Please make sure you see where that came from. Instead of dividing by negative 1/2, I'm multiplying by negative 2. We put plus our constant of integration. Now I need to solve for that constant of integration. Unlike the previous problem, you can't just use whatever number is there. It's not that easy. If you plug a 25 in, you'd say, well, that 25 to the negative 1/2 power, that means it's the square root of 25 in the denominator. That's where I got the negative 2 over 5 from. Plus c has to equal 2. Well, I know that 2 is automatically going to be 10 over 5. I'd have 10 over 5 plus 2 over 5. C is going to be 12 over 5. I get my first derivative. Now I take that first derivative and work backwards towards the original function. If I integrate this, t to the negative 1 over 2 is going to become t to the positive 1 over 2 when I add 1 to the exponent. If I divide the coefficient by 1/2, negative 2 becomes negative 4. I add 1 to the exponent on the understood t to the 0 in this one, becomes 12/5 t to the first, plus your constant of integration. Now, this is my original function general term. I need to get the specific. What's the value of c? Well, I know f of 25 is 3. Plug a 25 into this. You would have negative 4 times the square root of 25 is 5, plus 12/5 times 25. I just went ahead and said 25 over 5 cancels down to 5, so that's 12 times 5, plus c is equal to 3. Now I know that these would sum to be just 8 times 5, which is 40. I'll have 40 plus c is 3, therefore c is 3 minus 40. I get the negative 37 there. So now I can say my original function should be negative 4t to the 1/2 plus 12/5 t minus 37. And since the original had fractional exponents, it would be expected that your answers should have fractional exponents. So I'll say for my first answer, the first derivative, negative 2, and then I'll have t raised to the negative 1/2 power, and then plus 12 over 5. For my second answer here, and I'll bring this back down just a little bit. For my second answer here, I need to put in that negative 4t to the positive 1/2 power, and then scroll out of the exponent, plus 12 over 5 times t, and then minus 37. Should be precisely what they want in order to check that. Yeah, absolutely. Now, that was the last of the initial value problems, you might be glad to know. And when I was going through the notes in the section, I said that there wasn't any problems like some of the notes I did towards the end, but I wanted to go ahead and look at them anyway. These last two problems are sort of like them. They're much easier than some of the problems I did in my notes and the lecture notes, but they're decent, I guess. When I look at 38 here, it says a water balloon is dropped from a high building, falls for 3 seconds before hitting the ground. Determine the velocity it is traveling when it is about to hit the ground, assuming that acceleration due to gravity is negative 9.8 meters per square second and no wind resistance. And use decimal notation, give your answer to 1 decimal place. Okay. So, you know, in the problem, it says acceleration due to gravity, and we should have already really known that, negative 9.8 meters per second every second. And so I can work backwards. The integral of acceleration, since the change in velocity with respect to time is acceleration, then the integral of acceleration gives me velocity. I can say, well, I'm integrating with respect to t, so it's just going to be negative 9.8 t. Technically, it'd be plus your original velocity. But please notice in the problem, it says the water balloon is just dropped, which means your original velocity is 0. So I don't have to worry about that. There is no value of c there, or if you put it, you'd have to put a plus 0. So I have, this is my velocity equation. Now, what is it asking? It's asking, determine the velocity at which it's traveling when is it about to hit the ground. Well, that's 3 seconds later. So just plug a 3 into your velocity equation, and you've got it. Negative 9.8 times 3 is going to be negative 29.4. That would be in meters per second. The platform already takes into account the units, so you don't have to worry about that. I'll just say negative 29.4 and move on to the next question. Okay, correct. Now, I know what you were thinking. You're thinking that that problem was too easy. If you're thinking that, I'm thinking that too. I don't like that question. The next one's a little bit better. Talks about a car traveling 19 meters per second. It's beginning to decelerate at a constant rate of 3 meters per square second. After how many seconds does the car come to a stop? So unlike the problems in my notes where you had to do unit conversions between meters per second or feet per second and miles per hour, it's giving you everything that you need here. You know that the deceleration is going to be negative since it's slowing down. So the acceleration function is -3. That's important here. Whenever you integrate that to get to the velocity function, you'd say, well, the velocity is always going to be -3 times t to the first power plus whatever your original velocity is. And it says in the beginning of the problem, a car is traveling 19 meters per second. Then it's beginning to decelerate at that initial time. So the original velocity is your value of c, which is 19. Now, I know that the car stops whenever the velocity becomes 0. So you just set this velocity equation equal to 0. You can say, well, that's just going to be when t is equal to 19 divided by 3. So I know that that's the number of seconds. It's 6 1/3 of a second. I'll just leave it as 19/3 there. And now the next question it's asking is, how far will the car have traveled before stopping? So when I thought about that, what I did is I said, well, if I need something about the displacement or position, I need a position function. So the position function is the integral of velocity. So I'll get -3t squared over 2 plus 19t. And then you would say, well, plus c. Well, what is c? C is your original position. And in this case, I need you to understand we want to allow the original position to be 0. And the reason for that, if we allow the original position to be 0 at the instant the brakes are applied, then you know that whatever time it takes for it to come to a stop, that's going to give you your stopping distance. So it's not just that I wanted, because I didn't know what the original position was, I needed that original position to be 0. So the position at time t is going to give me the stopping distance. It's going to go from a distance of 0 to whatever distance it travels before it comes to a stop. I already know it takes 6 1/3 seconds or 19/3 seconds to come to a stop. So I just plug that into my position function. The -3/2 times 19/3 squared plus 19 times 19/3, just plugging it into that equation. I did that on the calculator because it says in the problem that it's wanting fractions. So you want to take your answer and convert it to a nice fraction, and we'll get your 361/6. And I'll check that. Absolutely. All right, guys. Hopefully this helps with this section. Please don't hesitate to contact me if you're struggling with anything. I'll be glad to help. Hopefully you're seeing that these problems are actually quite a bit of fun, really. All right. We'll meet back for section 5.2.